Good morning, everyone, and welcome to math class, lesson 76. And this lesson is one that's a little odd, and I wanted to talk to you about it. I kind of dreaded it also because it's kind of hard to do with on the computer, I felt, and I'm not as comfortable with doing the blackboard as what Miss Giles is doing. Anyway, and then my computer, not my computer, this program crashed on me. And so I lost everything I already recorded for you. So we're going to record it again. I made a couple of improvements as well, so that's okay. So let's talk about functions of negative x. And so here I've drawn a function, just an oddball function. This is why I didn't want to use the computer to do it, this part of it. But what we're going to do is look at x and negative x. So if you look at this particular function, if you go x to the right or negative x to the left, your result is the same y value. The y value on positive x and the y value on negative x is exactly identical. They're the same. It works out the exact same way. This is important. So negative, positive, if you go to the right a certain number or if you go to the left a certain number, the y value you get is exactly the same. That's also true for this x value. You're going over a little farther, but you get the same. Now it's a negative y value, but it's the same negative y value. It's exactly the same. It's upside, it's the same value, goes down the same amount. Whether you go x to the right or x to the left, positive x or negative x, you get the same y result. Here, when you go to the right x and to the left x, you get the same length of arrow, but the one arrow is up and the one arrow is down. So if you go right, you get a positive y. If you go left, you get a negative y, but it's the exact same value, okay? Magnitude, the same amount, but opposite sign. So when you go positive x, you get a positive y in this case, in this particular example, and in negative x, you get a negative y, but it's the same length of arrow, same size. On this one, when you go positive x, you get a negative, you get y. I'm calling that y still. That's the y answer if you go to the right. If you go to the left, you get the opposite of it. Now, in this case, y is negative and negative y is positive, but the point is whether you go to the right or the left, you get the same magnitude, but they're opposite signs. One's negative, one's positive, or one's negative, but they're opposite signs. Okay, so when you go left or right, you either get the same answer or you get exact opposite answers. Now, these are obviously special functions. These special functions are called even and odd functions. In an even function, like the first example I gave you, f of negative x is exactly the same as f of x. Here, that's the y value. F of x f is the y value, okay? So they're using functional notation, but that's the y value. So f of negative x and f of x are exactly equal. Whether you go left or right, you get the same answer. This makes it symmetric around the y-axis. If we go back, let me see if I can do that real quickly for you. If we go back to this original function here that I showed you, you'll see that in fact, it is symmetrical around the y-axis. It's kind of obvious. You can see that. If you remember being symmetrical around y-axes. Now the odd functions, f of negative x is the same as the negative of f of x. So if you put a negative number, the opposite number into the function, you'll get the opposite number out. Same magnitude, but opposite signs. And these are always symmetric around the origin. And again, if I go back to that graph, that original one that I showed you of this type, you can see if you rotate that 180 degrees around the origin, you'll get the same graph. And that's what we mean by symmetric around the origin. So even functions are symmetric around the y-axis. Odd functions are symmetric around the origin. Now, these are special, okay? Not every function works like this. You'll get some that are not even and not odd, okay? But if these two things work, then they're either even or odd. And you will have some that are both even and odd, just for the record. There are some of those really bizarre ones that are both even and odd. It is possible. Okay, so let's go on to a special example of this, and that is sine and cosine. The top one is cosine, bottom one is sine. If you look at the cosine, you should recognize that as an even function. Okay, you should see that as an even function because whether you go left or right, you're going to get the same y value. The sine, the lower one is the sine. That one is an odd function. If you go left or right, you get opposite but equal answers. Equal in magnitude but opposite in direction answers. So the cosine is even and the sign is odd. Now, the reason they're teaching you about even and odd functions is specifically to talk about cosine and sine. And so this is how these work out for the trig function. Sine is an odd function. That means the cosecant, which is 1 over the sine, is also an odd function. Cosine and secant are both even. Secant is just 1 over the cosine, so it is also even. So cosine and secant are even. And then tangent and cotangent are both odd also. And that's partly, that is because the tangent and cotangent are sine over cosine or cosine over sine. And so because of that, they become odd. So of the trig functions, 4 of them are odd, 2 are even. Cosine and secant are even. Okay, that's the one thing we need to teach you. That's going to come back later. Second thing. The second thing is functions of the other angle. Okay, let's look at this and see if this makes sense to you. We have the normal triangle here. And we have sine of theta. Okay, sine is opposite over hypotenuse, so it'd be y over h. Now, if we did the cosine of 90 minus theta, now I should point out to you that should be obvious to you that the other angle is 90 minus theta. The triangle adds up to 180. The right angle is 90. The other two angles add up to 90. So if one angle is theta, the other angle is 90 minus theta. That's how we would find it. That we're just labeling it that way. So the cosine of the 90 minus theta angle, the cosine is adjacent over hypotenuse. That would be y over h. You'll notice that the cosine and of the 90 minus theta angle and the sine of the theta are the same value, y over h. Okay? Now if we do cosine of theta, that's adjacent over hypotenuse, that's x over h. Then if we do the sine of the other angle, the 90 minus theta angle, that's opposite over hypotenuse, that would be x over h also. So the cosine of one angle and the sine of the other angle are the same. The sine of one angle and the cosine of the other angle are the same. Now, 90 minus theta, if you remember from our problems, that's a complement, right? An angle and its complement add up to 90. When we've done these in word problems and they say the complement of the angle is, we say 90 minus theta. Okay, so that word complement comes in here, and these are called complementary angles. And so that's the complement of theta. And that turns out to be where some of these words come from. Cosine actually means the sine of the other angle. The other angle is the complementary angle. So it's the complementary sine. So cosine means sine of the other angle or complementary or the complementary angle. Cosecant means secant of the other angle or the complementary angle. Complementary has a CO at the beginning of it. So this is the complementary function. Cotangent is the tangent of the complementary, the other angle. Okay, is this important? It is important because we're going to use this in the next section, but it also helps you know where these names came from. Cosine is literally the sine of the complement. So it's kind of an interesting concept. That doesn't really matter for what we've done previously. It will matter for things we're going to do in the future, because what we're going to do is what they call trigonometric identities. Now, in trigonometric identities, they're going to give you two expressions that have the same value. They're going to say this complicated trig thing equals this complicated trig thing, and they want you to prove that they really are. Okay, so you're going to give you two trig statements. They may not be complicated. Some of them may be fairly simple, but they could. But they give you two trig statements, and they tell you they're equal, but you have to prove it. The way you prove it is by simplifying it, and when you get done, both sides will be identical. You'll have a simple trig thing that is equal to an identical simple trig thing. Now, that's what trigonometric identity is. They're going to give these to you, and they're going to call this they're going to call this the rules of the game. And these really are games, and these are really hard to teach because every single problem is a little different. So you kind of have to just play it. You have to kind of monkey around with it. They recommend substituting, multiplying, and adding, and I'll show you how to do that in a couple of examples here. This one I chose to do on my sticky notes because it's hard to do the fractions clearly on the computer. So they give us this problem. Cotangent x over cosecant x equals cosine x. Now, if you want to follow along in your textbook, which isn't actually a bad idea, we're on page 469. Okay, so we're going to usually play with the left side and leave the right side alone. That's general process. Not a rule, just generally how we do it. So the cotangent is cosine over sine. Now, see, this is going to stretch your knowledge of trig because you've got to know all the various connections between the trig things. So cotangent of x is cosine over sine. Cosecant is 1 over sine. So I've substituted. That was the first step, right? Substitute. I substituted in place of the cotangent and the cosecant, the simplified cosine and sine versions. Now we multiply the numerator and the denominator by the reciprocal of the denominator. Denominator cancels out. The sine cancels out of the numerator, and you just have the cosine of x, which we are told is equal to the cosine of x, which it obviously is. And I put my big check mark there to show that we finished. We succeeded. We did what we were trying to do. Okay, let me give you another example. I can give you a couple more examples. So they start out with sine times the cotangent of x, and they tell us that that's going to equal 1 over the secant of x, and we have to prove that. So the first thing we do is substitute again. In place of cotangent x, we write cosine x over sine x. And again, it's a little harder to show on the computer, but if you can space it on your mind or write it out yourself, you can see that the sines are going to cancel. And then all you have is the cosine of x equals 1 over the secant of x. Well, the secant of x is 1 over the cosine, so the cosine is 1 over the secant. So yes, 1 over secant x equals 1 over secant x. It worked. And I don't have an easy way to make a check mark there, so I didn't. But then I would put a big check mark next to it because I checked it. By the way, you're not circling answers on these. The entire box is your answer, and the check mark is kind of your conclusion that you did, in fact, reach the end of the problem. Okay, this one brings in the stuff we just learned in this lesson. Cosine of negative x times sine of 90 minus x equals cosine squared x. Well, cosine of negative x is... Cosine is an even function, so the cosine of negative x is the same as the cosine of x. The sine of 90 minus x, that's the complement. That means that's the cosine of x. So cosine x times cosine x is cosine squared x, which equals cosine squared x. Check mark. We did it. Okay, these can be really intimidating, and I anticipate answering a lot of questions. However, don't panic about them. You can do them. What you have to do is simply harness all of your knowledge of trig functions and pull them all together. Okay? And so they give you, I'm sure they're going to give you several of these today. No, they give you 3. Very similar to ones we just did. Okay? So if you need to, as you're doing your homework, come back to this slideshow. Check the lesson out again. The book has them as well. Okay? But... good luck. I hope these work out for you. They actually can be a lot of fun if you can get a hold of the idea and do puzzles with them. If you like doing mind-bending puzzles like Sudoku or whatever, if you like that kind of thing, this is that kind of thing. You're going to enjoy these. And if you don't like that kind of thing, you can still enjoy them. It's up to you. But anyway, thank you all. Have a good day, and we'll talk the next time we have a tough lesson.